Hi, this is Roger from Kanka Labs with a follow-up video about the analysis of this fake Hakko FX-951 station, and we'll do some more measurements and circuit analysis and find some suggestions for improvement. Now, the first thing I was suspicious about was if this transformer can really deliver 70 watts. Now, to test this, the Hakko solder tips have a nominal resistance of 8 ohms, and so we just simply have to measure the RMS voltage when the heater is fully turned on. So we'll just turn this on and take a single shot measurement and see what we get. So the error message you could hear was simply when the temperature is a certain value below the set value, there appears a programmable alarm. And so now here I've catched a full turn on wave, and we get an RMS voltage of 21.6 volts. Now let's see what this gives in watts. Let's turn it off in the meantime. So 21.6 squared divided by 8 ohms gives 58 watts. So this is relatively okay. That's around 10 watts off from the nominal value of 70 watts. So I think we can live with that. But anyway, this transformer does not deliver a full power of 70 or even 75 watts, but the discrepancy, we can live with that. So the next thing to test is the accuracy of the temperature. So the next test is to measure the accuracy of the temperature setting, which I'm quite doubtful of. I will measure two extremes, the lowest and the highest setting. So let's start with 200 degrees Celsius. The iron has heated up for a few minutes, so the temperature should be stable now. Let's see what we get. So around 180. So we're 20 degrees on the low side. That's quite a lot, but would be still acceptable if at least the repeatability of this thing is okay. So let's remember this 20 degrees on the low side. And now comes the hard part of setting it to with the strange keycard to the highest value of 450 degrees. And let's wait a bit until it has stabilized. And in the meantime, we can measure how the temperature is rising here on the solder iron thermometer. So we're getting nearer to the set value. And unbelievable, that is nearly bang on. And by the way, so this is quite okay. So let's make a third measurement of 350 degrees, which is the usual setting for most of the solder work. So of course now takes some time until it is cooling down. And by the way, I've inserted a fresh sensor so that we get really exact values. And I've tested this also fake Hakko FG-100 clone in another video, and it was really very precise, up to 1 or 2 degrees Celsius with 2 other thermocouple thermometers. So it looks like here we are still in the range of 15 degrees low. So it looks a little bit, they have calibrated this thing at 450 degrees Celsius. And yeah, let's say that this is 15 degrees too low. So either there's something wrong with the circuitry or with the calibration or with both. But before we go on to a little bit of circuit analysis, so we're nearly here also 20 degrees low, between 20 and 15 degrees. Before we go to the circuit analysis of the analog part, how they measure the temperature and what's perhaps wrong with that, let's test 2 other safety features. The Hakko warns you if either you have no or a wrongly inserted solder tip. So if there's no solder tip, let's see if it recognizes this in action. If I pull the iron out, no, apparently it doesn't do this, but it should give an error message when we turn this thing on again. Yeah, now this is the error message if you have no solder tip inserted. And you can also, let me take another one. Yeah, you could insert a solder tip this way so that the heater is shorted out. I don't know if this is really something that occurs in real life, but in theory it could be. And the original station recognizes that now the resistance goes down to 0 by measuring the current, and let's see what this station does, even with the danger of destroying the power triac. If it recognizes this, and no, it gives strange display values, and you can see when it tries to turn on the heater that the brightness of the 7-segment display goes down, certainly because the voltage on the transformer goes down, but it has no direct way of detecting a faulty inserted solder tip. So I don't think this is really such an important feature, but anyway, to be 100% sure, the people at Hakko had a provision to display this wrongly inserted solder tip. Okay, let's first of all take a look at the original Hakko FX-951 PCB and guess a little bit about the circuitry. Now, one viewer of the first video pointed out to another video where the original FX-951 station was torn down, and this is a screenshot from that video about the PCB, and we can see it's a totally different circuitry. Let's start here. We have a bridge rectifier, so obviously Hakko is not switching the AC voltage from the transformer with a triac, but instead they are using a MOSFET to switch the rectified AC voltage. They have a different controller, and what we can see here, this is a little 10 milliohms shunt resistor, so obviously they are able to measure the current, and there's also a precision op amp, an OP77, I think it's either this one or this one, and that is probably used for the temperature measurement with the thermocouple integrated in the tip. And so this is a totally different circuitry, and here with this shunt resistor we already know how they manage to detect a reverse inserted solder tip, which of course gives a short, and I will link in the video from the fellow video blogger who did this very nice teardown and test and review of the original Hakko station. But now let's go over to a detailed circuit analysis of the fake Hakko station, especially the analog part. Okay, the first part of the analog circuitry was how the heater inside the tip is switched on. As you might remember, it was switched on with a triac, which in itself again was controlled by an optotriac, and the LED inside the optotriac was simply connected to a pin of the microcontroller. Now they've chosen an MOC3023. In the other solder station that I reverse engineered, the ATTEN AT-80D, they choose a similar way to control the heater, but they choose a zero switching optotriac, which means that the triac only turns on when the AC current is at 0 volts. And I don't know why they didn't use this one here. It was even a similar model. It was the MOC3043 instead of 23, so that might cost a few cents more, but it's good practice to use zero switching optotriacs so that you get less EMI. And so this could be an easy way to kind of upgrade this here by replacing the pin compatible optotriac with a zero switching optotriac. Now remember that the tip has two elements integrated. It has the heater with a nominal resistance of 8 ohms, and in series with that is a thermocouple which does not measure the temperature at the tip, but it does measure the temperature at the heater. And at an average temperature of 300 degrees Celsius, and let's assume this would be a type K thermocouple, this would give 42 microvolts per Kelvin output voltage, which of course you can only measure at times when the triac is switched off. So that we have a kind of open circuit here, then we would get a DC voltage here from the thermocouple. But remember, you have to multiply this with a factor to get the temperature at really the solder tip. In two different stations that I checked this, this was a factor of 0.7 or 0.5, but these were indirect heated solder tips. Now at these direct heated solder tips, the thermal resistance from the heater element to the solder tip is certainly much smaller. So I tried to check this here, and the factor is around 0.8. So you don't get really 42 microvolts per Kelvin for the temperature at the solder tip, but you get something around 30 microvolts, between 30 and 35 microvolts per Kelvin to get the temperature at really the solder tip. You always have to bear this in mind, because that was one of the faults of the ATTEN solder station. They simply assumed a 0 ohm thermal resistance from the thermocouple to the solder tip, and that's of course not correct. So let's go over to how the temperature is really measured, how they're doing it with a simple standard dual op amp. So one thing I did wrong in the first video, I thought that here, this part where 5 volts supply voltage is injected via a 10K resistor to tier the 200 ohms resistor to the input of the op amp, that this would be for cold junction compensation as they did in the ATTEN station. Just a short explanation, a thermocouple can only measure the difference between its hot end, which is the sensor end, and the cold end. That's where it's where the two wires are soldered to your PCB and to your analog measurement circuitry. So you need a second temperature sensor to measure the temperature here, so that you have to add the temperature here at the cold junction plus the measured temperature at the hot end. Now in the ATTEN station they simply assumed a constant temperature of 23 degrees Celsius, which is of course quite near to what you probably will have in your lab. But depending on where your lab is and what season you have, it could also be perhaps only 10 degrees Celsius in an unheated lab, or it could be something around 35 degrees Celsius if you're living in a hot region. So that's why you simply have to have here near this solder junction on your PC, you have to have a second thermal sensor for the ambient temperature at the so-called cold end or cold junction. But if you do the math, well, if we want to add something like 20 degrees Celsius and we have 42 microvolts per Kelvin, that would give around 1 millivolt of added voltage. Now let's see if we really get to 1 millivolt. We have a voltage divider of the 10K resistor and the 200 ohms resistor plus the 8 ohms resistance of the heater. That gives around a voltage division ratio of 1 in 50. Now 5 volts divided by a factor of 50 gives around 100 millivolts and not 1 millivolt. So clearly this injection of 100 millivolt has nothing to do with cold junction compensation. It serves a different purpose, and that is simply to detect when we have a broken or non-connected solder tip, because then we wouldn't have a voltage divider, because then here we have open circuit and the full 5 volts are present at the positive input terminal, the non-inverting input of the first op-amp. And of course, because this amplifies around by a factor of 28, we would get a clipped output to the positive voltage and a clipped output at the second op-amp. So the ADC in the microcontroller will recognize, aha, we have a full voltage here, much higher than anything we would get from our solder iron. So there must be a either broken or non-connected solder iron. And if we insert the right value of the 8 ohms, then we would get 100 millivolts here as a kind of DC offset. And of course this can only be detected at the moment when the solder station is turned on, when we still have no large thermal voltage here present, because if we get to relatively high temperatures, we also get relatively high output voltages here. So the microcontroller cannot discern when the station is in use if you have pulled out the solder tip or something like that. So that's not the perfect way to detect a either broken or non-existent solder tip, but anyway, better than nothing. Then one viewer commented, had a question, well, why is it necessary to limit the current into the positive input terminal? Because op-amps have an input resistance in the megohm or gigohm range. Well, yeah, that's true as long as the voltage is not higher than the positive supply voltage or lower than the negative supply voltage. But remember here, most of the time we have our 28 volts AC present, which gives a peak voltage in the range of 30 volts, and that is of course clearly higher than the positive supply voltage, or it could be minus 30 volts, which is of course much lower than the negative supply voltage, which is ground. So we have to limit the current, otherwise the input transistors of the op-amp, which is a bipolar op-amp by the way, the LM358, we have to limit the current. Now allowed is a maximum input current of 50 milliamps, and let's just do the math with, let's say the highest voltage could be 35 volts peak, and divide this by the maximum allowed input current of 50 milliamps. That would give us a minimum input resistance of 700 ohms to limit the current. So they choose 1.5K. Now you might ask, why don't they use 10K, 100K or 1 megohm to give a better protection? And why do they come with 20 or 25 milliamps through this 1.5K resistor? Why do they come relatively close to the maximum allowed input current? Now the answer is quite simple. Because this is a bipolar op-amp, we have a relatively large bias currents usually flowing out of the op-amp. And now let's see from the datasheet, we have 45 nanoamps flowing out of the input terminals, or into, it doesn't matter, and they flow through the 1.5K, the 200 ohms resistor and the 8 ohms. So let's add this up to 1.7K, and this of course gives an offset voltage generated by the by the bias current and the action of Ohm's law when a current flows through resistors. So let's see what 45 nanoamps multiplied by a total resistance of 1.7K, what that gives. And this gives us 76 microvolts. And 76 microvolts is already an offset of around 2 degrees Celsius. So we already get a constant error of around 2 degrees. Now you could, of course, null this out in software if you would know the exact value of the bias current, but an offset of 2 degrees Celsius is tolerable. So you have to make a compromise. You want to make the input current limiting resistor as large as possible to get as low as possible input currents when you have overvoltage or undervoltage. But you want to make it as low as possible to give you a low offset voltage generated by the bias currents. And so 1.5K is quite a good compromise. So that's the purpose why you need this resistor here and why they choose this value. Okay, now we have the problem. We have around 100 millivolts constant offset generated here plus the thermal voltage. So we have to get rid of this 100 millivolts again. And that's the purpose of this strange circuitry here. Now we'll make use of the superposition principle, which we already made without mentioning it here. We just look at the circuitry first as if the output here would be non-existent. Now let's see what we get here. We have 5 volt, a 100K resistor, and here again a voltage divider with this 100K of 2K plus whatever this 10-turn trim pot is set to. In fact, I've measured it, it's set here at 125 ohms. So we get a voltage divider again nearly in the same ratio as here. Here we have 10K and 208 ohms, and here we have 100K and 200 plus X ohm. So this is in fact not a scale adjustment, but it's the offset adjustment, because we have 2 offsets, or 3 in fact. We have the offset by this voltage divider, here the constant offset. Second, we have the offset from the bias current here, generating an offset voltage through R7, R5 and the solder iron. And we have, of course, the offset voltage of the op-amp itself, which is between 1 and 2 millivolts. And all these 3 add up here, and so that's why we need not this scale adjustment, but the offset adjustment. So that is when you look upon the circuitry as if the output of the op-amp would be non-existent, so that would be open circuit. Then we only have this voltage here. So at this point we have 100 millivolt plus X. Now let's look upon it the other way around. If this voltage would not be present, and that's what you do with the superposition principle, you only look at one voltage source and the others are open circuit. Now what do we have here? Now we have a simple non-inverting amplifier, and the amplification factor is, here we have this 100K resistor, and here we have this string of 3 resistors, 1.5K, 2K, and whatever the 10-turn trim pot is set to. And now here's the problem. This trim pot mainly trims out the total offset of the op-amp. but because it's in the voltage divider for the gain factor that is set, it also changes the gain factor, and that is of course not how you would do it. So when you change the value of this trim pot, you change the offset as well as the amplification. And that's a bit strange. They tried to get away just with 2 amplifiers and with 1 trim pot, but that's not how you should do it. So that's also the reason where the temperature error came from, because every op-amp you buy has a different offset. You can trim out the offset, but then you get a wrong scale factor. And with the setting that I measured, 125 ohms, you get a gain of around times 28. And well, the second op-amp is just clear. It's another non-inverting op-amp with a fixed gain of 11 with the 100K and the 10K resistor divider. So that is all to say. It's still, although the circuitry of course has 2 big problems: no cold junction compensation, or they do it in software with a constant offset, just add it in software. And the second is this combined scale plus offset trim pot, with which you simply cannot fully null out both factors. So how could we improve here? Perhaps one thing we could do is, instead of using the cheap LM358, we use a precision op-amp with an offset of, let's say, only 100 microvolt, which would give you a maximum error of 2 degrees Celsius. And with picoamps input, then we could first of all enlarge this resistor to give extra protection, and we wouldn't have to consider the offset, neither the offset voltage nor the offset introduced by the bias current, and then we would get at least reproducible results. So we only have to trim out this 100 millivolt generated here, but we always get then the same scale factor, and because this will always be set to exactly the same value, whatever op-amp you use, as long as it is a precision op-amp with ultra-low offset and ultra-low bias currents. I've already ordered a few different types that might fit. They don't cost today a lot of money, so perhaps that could be a second easy upgrade, just desoldering this dual op-amp and replacing it with a cheap precision op-amp. But there's not much more you can do. All the other things you could do have to be done in software. You could also, of course, make a 2-point adjustment in software, but, well, I like it more to have the analog circuitry just to be as good as possible and doing not any software calibration. So I think that was it for today, and I've decided I will try to write my own software with an Arduino Nano or Nano. I've already ordered one, and I can't tell you how long this will take, so don't wait for an improved firmware for this thing in the next few weeks. Just when I get done with it, I will post a video, and of course this will be open source when it's ready, so you can improve your own cheap Hakko clone. So that was it for today. Thanks for watching. Until next time, bye from Roger, bye from Kanka Labs.